Okay, we're going to try recording again and see if you guys like it a little bit better this time if I talk slower and I've made the screen bigger. What I want to talk to you guys about today is vector components, or components of vectors. And it's an important concept to learn for a number of reasons. It helps us solve vector problems at right angles, as well as when we start to solve them at non-right angles. We use vector components to do that. So every single vector, regardless of its direction, has a horizontal component and a vertical component. So even if you just have a horizontal vector, like just a vector like this, that's 10 meters east, it just has a horizontal component. So you would write that as dx equals 10 meters, and for that particular vector, dy would equal 0 meters. If you had a vertical vector, so let's say 10 meters south, like this one, that one has no x component. Right, so there's no horizontal component to it, and its vertical component would be 10 meters, but not just 10 meters, it would be negative 10 because it's in a negative direction. So when we're doing these vector components, we need to remember our directional justification. North and east will be positive, and south and west will be negative. Okay? And when we're doing these, it is extremely important and very helpful if you always draw the horizontal component first. It just makes it easier to memorize. If you always draw the horizontal component first, then to find the x component, you're going to take whatever vector. So if you're finding like dx, you would take the displacement and times it by cos of the angle. And for the y component, you would take the displacement and find sine of the angle. And this will make a little bit more sense when we actually do some examples. So you want to pay careful attention to the direction of each component, because once you've found the components, you need to make them positive or negative depending on if they're north, south, east, or west. So we'll just do an example of finding components here, and I've tried to include, or I have included vectors in all 4 quadrants. So just to sort of remind you in terms of quadrants here, so not only is north and east positive and south and west negative, this is, if we remember from math, this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. And in quadrant 1, both the x and the y are positive. In quadrant 2, the x is positive and the y is negative. In quadrant 3, both components are negative. And in quadrant 4, x is negative and y is positive. And that should make sense just in terms of what the cardinal directions are there on our compass rosette. So our first vector here is 115 meters, 32 degrees north of east. So north of east is in quadrant 1, okay, so it's over here. So I'm going to draw my resultant, because that's what this is. This is your resultant. That's basically what that is. So we're kind of going backwards from what we did before. So we have 115 meters, and that's at 32 degrees north of east. So we can draw on a horizontal component, and we can draw on a vertical component. And so then this becomes the horizontal component of that vector, and this is the vertical component of that vector. And you just use trig. And basically what we're doing, I'll show you what's going on, but then you can take this shortcut. If we look at that angle of 32 degrees, cos of 32 degrees is equal to dx over 115 meters. Okay, so that just makes dx equal to 115 meters times cos of 32 degrees, okay, which we can then calculate, and we'll get positive 97.5 meters. It's positive because it's east, right? So then we can change this here, and this, if we have sine of 32 degrees, that's going to be equal to dy, right? Because dy is the opposite of our hypotenuse is sine. What I'm just showing you is you don't have to show this step here. You can just go right to doing the resultant, which is the 115 meters times the appropriate trig ratio, sine 32.0 degrees. And so in this case, you're going to get positive 60.9. So and as long as you've drawn your horizontal component first, x is always cos and y is always sine. If you draw your vertical first, then they'll switch. So if you just make sure to always draw your horizontal first, you're not going to have any issues with that. So example B here, 13.1 meters per second at 79 degrees north of west. So north of west is in quadrant 4. Okay. So that's drawn this way, sort of in the opposite direction almost, as or the symmetric direction as the other one. This is 13.1 meters per second. And then this is, that's the x component of the velocity, and then this is the y component of the velocity. Okay? And this angle in here is 79 degrees. So Vx is going to equal 13.1 meters per second times cos of 79 degrees. And Vy will equal 13.1 meters per second times sine of 79 degrees. I should have put 79.0, but that's okay there. Your x component is going to be negative because it's west, and your y component will be positive because it is north, and then you just calculate those values, making sure you're in degree mode, right? Make sure you're in degree mode. Whoops. That's important. If you're in radian mode, you're going to get kind of funky answers. So the x component is negative 2.5 meters per second, and the y component is 13 meters per second. And that's pretty straightforward. Those are fairly easy ones to do because it was easy to figure out where the angle was and how to draw the resultant vector. You have to be careful in an example like C where we're given east of south. So what that actually is, east of south, is down here, right? So this is east of south here. So this would be 61.0 degrees east of south. This is south and this is east. We want to be able to draw our horizontal component of that vector first, right? So we want to draw horizontal, then vertical. There's the resultant, the F net. So F net is 72.5 newtons. This would be the x component of the force, and this is the y component of the force. But what we have to notice here is that the angle that we put in here is not 61 degrees. 61 degrees is the complementary angle, or supplementary, whichever one that is. What's going to go in there is 29 degrees, because 29 plus 61 gives us 90, and that's a right angle that adds up to 90. So this has to be 29.0 degrees in there. And then Fx is going to be 72.5 newtons times cos of 29 degrees. Okay, and that's east, so it will be positive, and that if we calculate that out, we get positive 63.4 newtons. And Fy is going to be 72.5 times sine 29.0 degrees, and that's going to be negative because it's south, and we get negative 35.1 newtons. Now I want to stress, you're not going to get negative on your calculator when you plug this in. You determine positive or negative based on which way the arrow is pointing. Okay. So this last one here is 218 degrees. So if we remember, this is using the navigation method. 0 is north, east is 90, south is 180, and west is 270. Right? You go clockwise around the circle. So 218 is going to be in there somewhere. So if that's 218 degrees, then this angle in here is going to be 270 minus 218, which gives you 38 degrees. Right? So this is 38 degrees, which makes the angle with the horizontal 52 degrees. So when we draw a diagram where we have the horizontal component first and then the vertical component, like this, this angle in here will be 52 degrees. This is our resultant velocity, which is 5.65 meters per second. This is the x component, and this is the y component. Then Vx is going to be 5.65 meters per second times cos 52 degrees. And that will give us a negative answer, negative 3.48 meters per second. And Vy is 5.65 meters per second times sine of 52 degrees. Sorry, had a little brain fart. Okay, and that's also going to be negative because it's south, so we get negative 4.45 meters per second. Okay. Okay, so if you need to take a bit of a break there to kind of get caught up, you can rewind and fast forward this video as much as you need to. We're going to move on to looking at relative motion with vectors, which sort of deals with components a little bit. It's still basically adding at right angles. It's just that it has some things in common with the components. So just to remind you a little bit about relative motion, let me just sorry, see if I can move that over here for a minute. Remember, relative motion is motion that's measured with respect to an observer. And so we talked about this before in terms of, you know, somebody walking on something that's moving, so somebody walking on a train or somebody walking on a bus that's already moving, and the speed they're going depends on if the person who's observing them is also on the bus or if the person observing them is outside. And so what happens with two-dimensional vectors basically is that sometimes objects move within a medium that is itself moving. So a plane flying in the air is affected by crosswinds, or tailwinds or headwinds, or a boat or a swimmer crossing a river is affected by a current. So we can look at different situations here with relative motion. An object that's moving with the wind or the current appears to be moving faster. So a plane flying with a tailwind is going to arrive faster. An object that's moving against the wind or the current appears to be moving slower. So a plane flying into a headwind is going to arrive later. And this just happens because if this is the velocity of the plane, right, and the velocity of the, remember we add vectors by going tail to tip, that's the velocity of the wind, then the actual velocity, or the velocity relative to the ground, is what we'll call that v ground, is actually longer. If something is moving, if we have the same plane, and that's the velocity of the plane, and the wind is a headwind, right, so it's moving against the wind is going the other way, like this way, and then what that does is that leaves a smaller velocity. The plane looks like it's going a little bit slower to somebody who's observing it from the ground. When you have an object that is moving perpendicular to the wind or the current, then its velocity is also going to be affected. And interestingly enough, its velocity increases significantly. So if you have a person swimming across a river with a current, so if this is the person, if this is, you're going across the river here, so this is the velocity of the swimmer, okay, going north, and say there's a current that's going east, then the velocity of the swimmer in relation to somebody on the ground, somebody who's watching the person swim, that velocity actually looks a little bit larger, right? It becomes the hypotenuse of the triangle. And so that's called the velocity relative to the ground, or velocity relative to shore, right? So velocity relative to the ground, or relative to shore, or whatever. It's relative to shore if you're talking about a river, relative to the ground if you're talking about a plane, but they both mean about the same thing. So we'll do a quick example that kind of compares these three different situations here. We have an airplane flies with an air velocity, so we can call that v air, or velocity of the plane. So v air is 810 kilometers per hour west. The wind has a velocity, this would be v wind, of 55 kilometers per hour. We're just going to look at the different ground velocities, or velocities relative to a stationary observer on the ground, for the wind blowing in these different directions. So if the wind is blowing west, right, so if we have the velocity of the air as being 810 kilometers per hour west, and the velocity of the wind is 55.0 kilometers per hour west, since the original velocity of the plane is west, we'll make west positive and east negative just for these first two parts of this example. But basically you have the velocity of the plane, or velocity of the plane in the air, and we're going to add to that the velocity of the wind. So the velocity relative to the ground, v ground, is just the sum of those. Velocity in the air plus velocity of the wind, which is just going to be 810 kilometers per hour plus 55 kilometers per hour. So not much different than stuff we've done already with relative motion. If now we're going to make the wind blowing east, okay, so now we still have our velocity in air is 810 kilometers, sorry, and the plane is flying west, so there's the velocity of the plane in the air. Now the wind is east, so that's the velocity of the wind. So the velocity, the overall velocity of the plane relative to the ground is going to look a little smaller. It's still the sum, the vector sum, velocity to a stationary observer on the ground is still the velocity of the plane in air plus the velocity of the wind. But the velocity of the wind is going to be negative now because it's east and we made east negative. So 810 plus negative 55 will give us 755 kilometers per hour west. It's still west, but it looks like the plane's going slower. The wind blowing south, so now what we have is we have the velocity of the plane in air is to the west, and the wind is to the south. So they meet at a right angle, so we have to use our skills at adding two-dimensional vectors that meet at a right angle, which means we make a right triangle, and the velocity of the plane to an observer on the ground becomes the hypotenuse of that triangle. So the velocity of the plane to an observer on the ground is still the vector sum of the velocity in air and the velocity plus the velocity of the wind, except that now, in order to do that vector sum, we find that vector sum by finding the hypotenuse using Pythagoras. Right? So it's the square root of 810 kilometers per hour squared plus 55 kilometers per hour squared, which gives us 812 kilometers per hour. And then we also have to find the angle, because it's a vector, and we always have to find angles. So when we have a right triangle, or we have to find a direction with a vector. So it's inverse tan of the velocity of the wind, which is 55 kilometers per hour, south, over the velocity in air, which is 810 kilometers per hour west, right, opposite over adjacent. And that's going to give us 3.9 degrees south of west. And, you know, the difference between the velocity in air and the velocity of the ground isn't a huge difference, because, of course, the angle is really, really small. There. Okay, so again, if you need to pause to catch up, that's fine. I'm going to move on to the next page, but like I said, you guys can pause and you can go backwards and forwards here if you need to. So we'll do just another example looking at some different types of questions or different types of things that you can be asked to solve for in a relative motion question. So it's very similar. A small sailboat has a velocity of 1.5 meters per second. It heads north across a river that's 1,200 meters wide, and that river has a current of 0.85 meters per second west. So we want to find the boat's velocity relative to the shore. So draw your vector addition diagram first. The boat is heading north. So there's north, 1.5 meters per second. And the current is west, towards the west. So there's the current, 0.85 meters per second west. The velocity relative to the shore is the hypotenuse, and we also need to find the angle. So the velocity relative to the shore is the square root of 1.5 meters per second squared plus 0.85 meters per second squared, which is 1.7 meters per second. And the angle is inverse tan of 0.85 meters per second north over 1.5 meters per second west, which gives us an angle of 30 degrees. Well, it's actually, I'm going to write down 29.5 because we're going to need that in a minute. 29.5 degrees, which with sig digs rounds to 30 degrees. In this case, west of north. Sorry, I did this wrong, didn't I? This should be west, and this should be north. Yeah, somebody pointed that out before I fixed it myself. See if you can convince the sub to give you a candy. The second thing we want to find is the time it takes a boat to cross the river. And for this, we're going to need the fact that we know that the river is 1,200 meters wide. So we're going to draw the same vector diagram as we drew in part A, like this. Okay. And we know that the river is 1,200 meters wide, right? Because the person starts here and they swim north across the shore, right? So the river, like it goes like this. Right, like that, and the current is flowing west. So that's 1,200 meters across the river. The angle that we found here is 29.5 degrees, and that's why I didn't want to round that. And we actually need this vector, this triangle, to also find the distance the boat lands down the river, because that's what we want. This is the distance downriver here, is what that horizontal component is the distance down the river. So in order to find the time it takes a boat to cross the water, we need to know the distance that the swimmer swims, right? Or that the boat goes, not the distance that the boat travels. That's what we need to know, is how much ground the boat actually covers when it goes across, because it doesn't go straight across this way, it goes across at an angle, so it's actually covering a little bit more ground, and that's why it ends up downriver. So we want to use velocity as distance over time, right? Which will then, time will be distance over velocity, where we don't know the distance yet. We're going to use the velocity from part A, 1.7 meters per second, and we need to know what that distance is. So to find that distance, we know the adjacent side, and that distance is the hypotenuse. So cos of 29.5 degrees is equal to 1,200 meters divided by d. So d is going to be 1,200 meters divided by cos of 29.5 degrees, which is 1,378.7 meters. So then that becomes our distance here, 1,378.7 meters. When we divide that by 1.7 meters per second, we get 811 seconds, right? Or 8.1 times 10 to the 2 seconds. We can also use a trig ratio to find the distance downriver. That 29.5 degrees, the distance downriver is the opposite, and the 1,200 is the adjacent. So tan of 29.5 degrees is equal to the distance down the river divided by 1,200 meters. So the distance that the boat lands down the river is 1,200 meters times tan of 29.5 degrees, which is 679 meters. But with 2 sig divs, it would be 6.8 times 10 to the 2 meters. Okay, and that's a lesson, you guys. Again, if you need to go back and replay any of this, just play the video again and let it run through, and pause and rewind, fast forward as much as you need to. If I don't see you by the end of the day, have a really, really nice break, and I'll see you guys when we get back on April 8th.